Assalamu alaikum. Welcome to Chapter 1, an introduction to text analytics. I am Oda Shukri and I'll be your guide through this attractive topic. Now you might be wondering, what exactly is text analytics and why should we care? In this presentation, we'll break it all down. The fundamentals, its real world impact, and how it's transforming the way we interact with data. So let's get started. What is text analytics? Imagine you are standing in front of a massive disorganized library. Millions of books, articles, social media posts, all filled with text. Text analytics is like having a smart librarian who can find patterns, extract key insights, and even predict trends from all that unstructured data or digital noise. Technically, it is the process of using statistical algorithms and machine learning to derive meaning from unstructured text, whether it is tweets, emails, or research papers. You might also hear that text analytics is called text mining or natural language processing. Now, why does this matter? Think about it. Text is everywhere. Search engines like Google powered by text analytics. Your email's spam filter, text analytics again. Even Netflix recommendation. So whether you realize it or not, text analytics is already shaping our digital life. Now let's talk about where all this text comes from. Picture a massive digital libraries like PubMed, backed with academic papers, especially in fields like biomedical research. Then there are electronic news platforms like Google News, which serves up fresh stories daily. And don't forget the web itself. Forums, social networks, hypertext. It's like an endless buffet of raw opinions and ideas. Take a Twitter, for example. Its short, informal posts give us real-time snapshots of public sentiment. All these sources fuel the incredible applications of text mining. Ready to see some examples? Let's go to the next slide. Text mining has countless applications across industries. For instance, ever type something into Google and been amazed at how quickly it finds relevant results? That's text mining hard at work, crawling and indexing web pages. Spam filters use text mining too. They not only block annoying emails but also infer your interest for targeted ads. News portals categorize articles into topics like sports or politics, while recommendation systems analyze your preferences to suggest products, movies, or songs. And businesses, they use sentiment analysis to understand customer feedback and make smarter marketing decisions. Before computers can understand text, we need to represent it numerically. How do we turn messy text into something machines can understand? There are two main ways: bag of words and sequences. The bag of words model treats text like a jumble or a chunk of words, ignoring order but counting frequencies. It's great for tasks like classification, but loses contextual information. On the other hand, sequence-based representations keep word order, capturing richer meaning. It's perfect for translation or summarization. Each method has its strength. Which one is better? Depends on the task. Bag of words works for topic modeling, while sequences excel in chatbots. So, what makes learning from text unique? Text data is huge. with vocabularies ranging from 100,000 to over a million words. Most documents uses only a tiny fraction of those words. Imagine a library where 90% of shelves are empty. It is sparse. Most words counts are zero. Kind of like trying to find needles in a haystack. This sparsity favors algorithms like support vector machines, which succeeded on sparse data. Plus, since word counts can be negative, we can build interpretable models like non-negative matrix factorization. Pre-processing is key to handle noise like typos and abbreviations, ensuring accurate analysis. Let's break down the analytic models used in text mining. First, pre-processing steps. Clean the text, removing HTML tags, stop words, and normalizing capitalization. Next, similarity computation helps compare documents. For example, grouping related articles or recommending content you will love. Dimensionality reduction techniques like LSA and LDA compress high-dimensional data into manageable chunks, like shrinking a giant spreadsheet into a neat or well-ordered summary table. Clustering groups similar documents, while classifications assigns labels. Advanced topics like transformers take this to the next level, enabling machines to truly understand language. Pre-processing is like washing vegetables. It's essential for preparing raw text. We start by extracting useful text, removing irrelevant bits like ads or code. Stop word removal gets rid of filler words like the and, which add little value. Stemming consolidate variations of words like run and running into their root form. Finally, frequency-based normalization adjusts word weights using metrics like IDF, ensuring important terms stand out. By the end, we clean, consistent text ready for analysis. Sounds simple, right? But trust me, it is the backbone of good text analytics. Similarity computation. Ever wondered how machines decide if two documents are similar? One common method is cosine similarity. It treats documents as vectors and measures the angle between them. Closer to zero, nearly identical. 90-degree, totally unrelated. Cosine similarity ensures the scores stay between 0 and 1, handling the high dimensionality and sparsity of text data beautifully. This technique powers everything from clustering related articles to recommending content you don't know you need. Handling high dimensional text data can feel overwhelming, like staring at a giant spreadsheet with millions of columns. That's where dimensionality reduction comes in. Techniques like LSA, NMF, and LDA shrink the data while keeping the most important features. For example, LDA might reveal hidden topics in news articles like sport, politics, or tech without any labels. And matrix factorization breaks down a document term matrix into smaller matrices, U and V, where U represents reduced document features and V represents latent topics. Not only does this reduce complexity, but it is also enhance interpretability, helping us discover meaningful topics. It's like turning a cluttered room into a tidy organized space. Text clustering groups documents based on their similarities. Unsupervised methods like k-means partition documents without predefined labels, while probabilistic models assign topics based on probabilities. Graph partitioning treats documents as nodes in a network, clustering them based on connections. These techniques are invaluable for organizing large collections. Imagine sorting thousands of tweets into categories automatically. Now let's talk about text classification. Imagine teaching a computer to sort emails into spam or not spam. That's what text classification does. It assigns labels to documents based on their content. Supervised learning models like naive Bayes and support vector machines learn from label training data to predict categories for new texts. Applications think spam detection, sentiment analysis, and topic labeling. Ever wondered how your email client knows which messages to flag as junk? That's text classification at work. The challenge is ensuring the model generalizes well to unseen data because nobody likes false positive. Here is where it gets even more interesting. In many cases, text is not analyzed alone. It's combined with other types of data. Think about social media posts that include both text and images or tweets that link to articles. Techniques like shared matrix factorization and vectorization machines help integrate these different data types. For example, analyzing a tweet might involve understanding its short, sparse text alongside meta data like hashtags, links, or user interactions. This joint analysis is crucial for applications like personalized recommendation or detecting trends in real-time streams. Ready to see how this ties into search engines? Keep listening. Information retrieval and web search. Ever wondered how Google serves up exactly what you are looking for in milliseconds? That's information retrieval in action. Tools like inverted indices and PageRank play a key role here. Web crawlers collect and store documents, creating massive databases that search engines query against. Ranking algorithms then prioritize results based on relevance, ensuring you don't have to go through irrelevant pages. Without these innovations, finding information online would feel like searching for a needle in haystack. And guess what? Machine learning models like ranking SVM make this process even smarter. Alright, now let's dive into sequential language modeling. Remember the bag of words approach we discussed earlier? It's great, but it ignores word order. Enter embeddings, like word2vec, which represents words as a vector in a semantic space. Imagine placing king and queen close together because they are related concepts. These embeddings form the backbone of modern natural language processing, enabling applications like machine translation, chatbots, and voice assistants. Core models like RNNs, LSTMs, and GRUs take this further by capturing context over time. This is how Siri almost sounds human. Transformers are the game changers of natural language processing. Unlike RNNs, which struggle with long sequences, transformers excel at handling context across entire sentences or even paragraphs. Pre-trained models like PEAR, GPT, and T5 have set new standards for performance. These models are fine-tuned for specific tasks, powering everything from question answering systems to advanced chatbots. Why does this matter? Because it is why tools like Google Assistants or language translators feel so spontaneous today. Now let's talk about text summarization. Have you ever skimmed the snippet under a Google search result instead of reading the full article? That is attractive summarization. That is extractive summarization, pulling out key sentences directly from the original text. On the other hand, abstractive summarization generates new sentences that capture the core of the content. News platforms use summarizations to provide quick overviews of lengthy articles. Recently, deep learning models like large language models (LLMs) have taken summarization to the next level, producing high quality and fluent summaries. Next hub, information extraction, turning messy text into a clean, structured table. This process identifies names of people, places, organizations, and even relationships between them. For example, when you ask Siri about apple, it knows whether you mean the company or the fruit, thanks to entity recognition. Information extraction is also the foundation for knowledge graphs, which help search engines understand connections between entities. It is core mechanism driving smart assistants and the question answering systems. Let's explore question answering, a key area in natural language processing. Ever asked Siri or Alexa a question and wondered at how accurately they responded? That's a question answering in action. This process tests how well a machine understands text by asking it questions and evaluating its responses. There are different types of question answering tasks. Factoid questions like what is the capital of Palestine, reading comprehension, and long form question answering. Why does this matter? Because it measures how well machines truly grasp human language. Real-world applications include chatbots, virtual assistants, and even educational tools that help students learn more effectively. Ready to see how this ties into understanding opinions? Let's move on to opinion mining and sentiment analysis, which focus on understanding people's opinions and emotions from text. For example, when you read product reviews online, the text often contains valuable insights beyond just star ratings. Sentiment analysis helps businesses figure out whether customers liked or disliked a product, while opinion mining digs deeper into what exactly they liked or disliked. This is especially useful in marketing, brand monitoring, and improving customer experiences. Here is where things get technical but attractive. Let's talk about text segmentation and event detection. Think of text segmentation as dividing a long novel into chapters. Each chapter focuses on a specific theme or topic. Similarly, text segmentation breaks down lengthy documents into smaller sections based on shifts in subject matter. Event detection, on the other hand, spots changes into topics across multiple documents, especially in real-time streams like social media or in news feeds. For instance, event during a breaking news event, algorithms can detect sudden spikes in mentions of keywords like earthquake or election result. Both techniques are essential for organizing massive amounts of text and staying ahead of rapidly evolving information. Here is where it gets exciting. How do we bring all these concepts together? Finally, to wrap things up, text analytics is a multidisciplinary field that combines natural language processing, machine learning, and information retrieval. It helps us make sense of the mountains of text data flooding our digital world, from tweets and blog posts to scientific papers and customer reviews. Pre-processing and representations are the backbone of effective text mining, ensuring raw text is clean and structured before analysis. Advances in AI, especially transformers and pre-trained models like BET and GPT, are developing how we analyze and understand language. Looking ahead, integrating text analytics with other data types, such as images, videos, and networks, will unlock even more possibilities. Whether it is helping you find relevant information faster, summarizing complex articles, or extracting actionable insights from customer feedback, text analytics is shaping the future of how we interact with data. Thank you for listening.